Let's go ahead and understand the next thing, which is reducing the load capacitance. Now, let's say there is an inverter which is driving another inverter. The output of this inverter is going to the input of the next one. So there will be in some load capacitance. I've approximated this load capacitance to be nothing but some interconnect capacitance. We already saw interconnects. So interconnects would have some capacitance and nothing but the gate of this guy. Correct? It's driving the gate. So C load is nothing but approximately equal to interconnect capacitance plus the gate capacitance of the next stage, or inverter 2 in this case. Now if we want to reduce load capacitance, we have to reduce interconnect capacitance or gate capacitance, and if we can reduce both, it would be fantastic. So interconnect capacitance are technically reduced by floor planning. Again, we are not going into the details of this. Floor planning can help us in reducing the interconnect capacitance. Floor planning will tell us exactly how do you want your circuit or your interconnects to be connected with different blocks on your IC. Gate capacitance. Now how can the gate capacitance be reduced? We know that gate capacitance is nothing but COX into W into L. So if I reduce the width of this guy, or we should not touch the length, because length is nothing but the process in which you are working in, or the technology in which you are working in. So I'm not getting into this, and this is a very important parameter when we go to analog designs. Currently, let's focus only on W. So when the W is reduced, the gate capacitance is reduced. That means the load capacitance can be reduced. But what will happen if I reduce my W? See, if I zoom into this, if I reduce my W, I know that ID is proportional to W, correct? Directly proportional, we have seen that. And we have also seen that R is inversely proportional to W. If that's the case, what's going to happen here is your R will increase if you keep on reducing the W, correct? And if R increases, your delay of this specific block, which is nothing but R into C, will increase. So this guy will become slow, correct? Now it's okay if one of the guys becomes slow. If suppose this is your circuit and this is your input and this is your output, and there are so many paths going from input to output, and the path which you are concerned with is this path, which is also called as a critical path, then in this path you should not make your circuit slow. But in rest of all the paths, you can definitely make your circuit slow because they are not your critical path. Again, critical path is a very interesting topic to understand. The worst case analysis from your input to the output, on basis of which you can find your frequency. Currently it's beyond the scope. What you need to understand is the delay is not, or you can slow down your transistors which don't come in your critical path. So that's okay, so that we can reduce the load capacitance and save on some of the dynamic power. So this is the second parameter. Let's quickly go ahead and see the third one, reducing VDD. Now we are going to have an exclusive clip on this where we will talk about how we can reduce power through voltage scaling, and at that point of time we will discuss about VDD as well. But for the time being, let's quickly understand, if we reduce our VDD, we know that dynamic power is proportional to VDD square. So that will help us in considerably reducing our dynamic power. Now I've written this just for your reference. I've derived this also in some of the clips previously, but you don't have to remember. What you are expected to know here is, if you look at the equation very closely, if you keep on reducing your VDD, what's going to happen is your delay is going to keep on increasing. So you will make your circuit very, very slow. So that's going to be a trade-off. And we will see whether that trade-off, depending on the application, whether it's a good idea to reduce VDD to a certain value or below it. So that's the third parameter, reduction of VDD. The fourth one is reducing the frequency, right? If you go ahead and see the equation, it was alpha, switching activity factor, load capacitance, VDD, and frequency. Again, if I reduce my frequency, I know that the time is, we know time period is inversely proportional to frequency. So reducing the frequency will increase the time period or the delay, and that will make my circuit slower. But in circuits where more than delay, which are concerned with throughput again is a detailed area of understanding. It means the rate of change of output, which is ideally the case in case of digital signal processing systems or in pipeline systems. So they are more concerned with throughput. So with such systems, you can go ahead and do this, and still it will help you in saving the power and give you a better performance, and you will not lose out on quite a lot. So I hope in this clip you have understood the 4 parameters ideally which contribute to switching power, which I have said here is a major part, and I have labeled this as dynamic power. So dynamic power is a combination of switching and short circuit, and we also saw how to reduce it. Hope you have followed. Stay tuned for further clips, and thank you very much.